Welcome to the Rich Report, a podcast with news and information on the world of big data. Today, my guest is from Gigaspaces. We have Uri Cohen. He is the Executive VP of Product Management at the company. Uri, welcome to the show today.
Thanks, Rich. Glad to be here. Thank you.
Well, thanks for coming on, Uri. I became familiar with Gigaspaces a number of years ago. I was at Sun Microsystems, and you guys were always our partners in the booth when we went to Wall Street. So it's great to have you on, and especially today because it seems like in-memory computing is just all over the place, and I think you guys were there at the start, weren't you?
Yes, actually, we started off about 12 years ago, and you rightly mentioned that we initially partnered with Sun, and a lot of our concepts are modeled after the Genie and Java Spaces specifications, which originate back to the late 90s and the early 2000s. And so essentially, we've built a platform based on those wonderful concepts, I would say, around distributed computing and discovery, and the way distributed systems and processes communicate with one another. And we're still kind of, using the same concepts today. Kind of the APIs have evolved and been modernized since, of course, but the basic concepts still hold in Gigaspaces and in other products as well.
Yeah. So you were doing this way before anyone was really talking about big data. So, well, hey, Yuri, I brought up your slides. Why don't we go into the presentation and we'll do a Q&A at the end?
Okay, sure. Okay, so I wanted to kind of go through first of all the motivation behind in-memory computing in general and how it's good for big data, and then dive a little bit into what we do at Gigaspaces, what our platform looks like, and how it can be useful for this. And this is actually taken from a survey that we conducted about a month and a half ago, and we surveyed more than 250 executives in the industry and essentially Fortune 500 companies. These are all CXO, IT managers, and people that typically control large IT organizations. And the question there was, do they implement real-time big data analysis? So when most people think about big data, they think about big volumes, terabytes, petabytes, and how to store them efficiently. But recently, it's not just about the volumes; it's about the velocities of this information and how fast it's coming into your system, and more importantly, how fast you can make sense of it. And the faster you can make sense of it, the more agile you are, the more competitive you are on the business side. So the question was here, does your organization actually implement real-time big data analysis? And interestingly enough, almost 80% said that they're either already implementing this or plan to implement this sometime in the future, which is a very large number. So everyone actually realized that this is important. And whereas 2 or 3 years ago, everyone were talking about Hadoop and how to store large amounts of data and then make sense of them offline in kind of a batch mode, today a lot of people are talking about how to process data as it flows into the system, how to make sense of it in real time. So it's not just about I got this huge chunk of data that I'm gonna mash into or I'm gonna process offline. Now I want to make sense of it as it flows into the system, and I want to take decisions based on that. So a few examples can be, for example, if I'm using Twitter for advertising, me as an advertiser, I want to know at any given point in time how my campaign is doing, right? Or if I'm publishing a certain product on my e-commerce website or doing a certain promotion, I want to know in real time what's going on, how the users are reacting to it, and so on. So the big web companies like Facebook and Twitter have been doing this for quite some time. It's becoming more and more dominant with other companies. This is actually taken from another survey conducted by a group called Ventana Research, and this also kind of indicates the real-time trend as far as big data is concerned. So you can see here, this survey is being conducted with about 240 respondents, again, IT managers, and it asked about their plans for big data technologies. And the interesting thing you can see here is that in-memory databases, ranked second here, is actually higher than Hadoop and flat files and RDBMSs, which means that the real-time aspect of things, and more specifically, using in-memory technologies to implement it, has become very dominant, and it's one of the primary challenges that people are facing today. Two other interesting things here. About 67% of the respondents here indicated that one of their biggest technical challenges is the lack of real-time with big data. So I mentioned Hadoop a bit, and it's probably something that most people that implement big data are already aware of. Hadoop is very good at congesting and storing very large amounts of data. But if you want to make sense of this data, typically what you would have to do is launch what we call MapReduce jobs, which can take anywhere from a few minutes to a few hours or even a few days. And in a lot of cases, that's just too late. Another interesting fact is that the report indicated that many of the organizations are planning to use in-memory databases. And for us, it's a novel thing. Back in 2007, 2008, we had to do a lot of market education so that people actually realize and understand in-memory computing. And a lot of people have a lot of prejudice about it. It's running in memory, so it's volatile. It's not highly available. It's not fail-safe, and all these kinds of concerns. On one hand, and on the other hand, it's also about why do I need this at all? So we're seeing that this is actually changing, and people are becoming more and more aware of these technologies. So I'm kind of going through a lot of kind of market trends and motivations before I dive into the technical details. The next slide, titled "Growing the Demand for Scalable Data Solutions," is actually taken from the same survey we've conducted recently. So this is also related to big data and real-time analysis of big data. There's a very common or important part of this domain, which is called stream processing. So if I'm looking at real-time big data analysis, it's generally speaking divided into two segments. The first one is stream processing, which I'm going to explain about in a second, and the second one is real-time ad hoc querying. Okay, so as far as stream processing is concerned, it's basically about making sense of data that flows into your system. So almost any enterprise or web-based system has data flowing to it all the time. Whether it's if we're talking about e-commerce websites, it's transactions and impressions and page views. If we're talking about financial systems, it's trades and it's market data information. If we're talking about, let's say, a monitoring system or sensor reception systems, like, for example, I know Homeland Security, which is connected to a lot of cameras and gets information from many different inputs. It's about receiving this data in real time and making sense of it in real time. And that's very, very important. So this is stream processing. The other bit, which I mentioned, is ad hoc querying. So ad hoc querying is very similar to what we always had with the relational databases, with two major differences. The first one is that the data itself is different. Okay, so this is kind of the variety aspect of big data. Big data is not as structured as traditional data has been. So it can be composed of any number of attributes. It can be actually not textual at all, or If it is textual, it doesn't necessarily have a predefined format. Okay, for example, user-generated content is something like that. And the other part is that it's much bigger, right? So it's about volumes, and when you're talking about ad hoc querying, making sense or implementing ad hoc querying on large amounts of data, typically terabytes, is much more challenging technically than doing so for smaller amounts of data, which is what relational databases typically used to do. So this is kind of the two aspects of real-time big data, and today I'm going to focus on the first aspect, which is stream processing and making sense of data as it flows into the system. So as far as this question goes here, you can see that again, almost 70, actually more than 70% of the respondents said that they're planning to implement stream processing as part of their architecture, either imminently or sometime in the future. So after seeing all these market trends and where kind of real-time big data is important, let's switch to in-memory computing and how that can help real-time big data. So this is a quote taken from Gartner's top 10 technology trends for 2013. It's actually last year, right? They still haven't issued the one for this year, but in-memory computing was actually one of these top 10 trends. And Gartner says it's providing transformational opportunities, right? It allows you to execute certain types of hour-long batches and processes within minutes or even seconds. You can scan and process literally millions of events, and a lot of our users are doing that. Hundreds of thousands or millions of events very, very quickly and make sense of them. And I mentioned before a few verticals that this can be relevant to. It started off, financial services were kind of the pioneers there. They needed to process a lot of transactions and a lot of market data ticks very, very quickly. But it's also very relevant to homeland security systems, for example, that receive a lot of sensory data and need to make sense of it very fast. If there's a threat, you wanna identify it very quickly. Web-based systems, again, if you have a campaign that you're running, or if you have a post that you published on your website, you want to know how people are reacting to it very quickly. If you're an e-commerce website and there's a product that is very popular, you want to know about it immediately. You want to know who is interested in it and what is the demographic profile of these users and so on. So making sense of data very, very fast is very, very important. And in many cases, if you want to process so many events simultaneously, the only practical way to do that is in memory. And that's because memory as a medium can be anywhere between 100 and 1,000 times faster than other mediums. And not only that, it's much more parallel. So you can run multiple processes simultaneously against the same data without really taking a serious performance hit, which is not really possible with other mediums. So this is a depiction of the technical advancements in recent years. I would say 2, 3, even 4 years for recent years. And it describes two types of advances. The first one is hardware, which I think we're all aware of, right? We feel it every day on our laptops and on our smartphones. We're switching to multi-core architectures, right? The typical server today ships with 8 to 12 cores, and you can get servers with 32 and 64 cores. So it becomes essential that you know how to parallelize your workloads. And if you want to parallelize disk access, that can be very, very challenging. So it's important to use mediums such as memory, which allows for that. It also talks about how the RAM itself, the capacity of RAM, is growing. It's not rare to see today 1 terabyte and 2 terabytes of RAM within one server board. And this is a complete game changer. It's something that you couldn't even imagine a few years back. It's complete workloads which were typically stored and handled on the disk because of capacity limits can now be loaded into memory and handled there much, much, much faster. The other interesting thing is networking. And the reason I'm mentioning that is because a lot of in-memory systems use the network, and more specifically data replication, as a mean to achieve high availability and fault tolerance. So instead of storing your data on only one server and then hoping that it doesn't fail, and we know failures do happen all the time, you replicate the data to at least one more node or one more server in your network for redundancy and high availability. And when you do that, the speed of the network becomes a very important factor, and that too has been increasing and improving very much in the last few years. It says here 25 gigabytes a second of data throughput. We've already seen 40 gigs with InfiniBand networks, and some of the companies, hardware companies, are talking about 100 gigs per second, gigabits per second of throughput. And again, that's also kind of changing a lot of the assumptions that we used to have about how we can share data between servers and hosts. So on the hardware front, I think you kind of realize that latest advancements are really enabling a whole new class of applications that can reside in memory and use the memory as the main storage medium. But there's also been some interesting advancements in software. I mentioned before that we as a company had some hard times about 5 or 6 years ago when we approached our users and our prospects and explaining to them about distributed architectures and non-relational data models, which we've been doing since day one. And I'm happy to say that more recently you can see a lot of these concepts and architectures all over the place when it comes to NoSQL databases like MongoDB and Hadoop and Cassandra and a bunch of other products. So concepts like columnary databases and document-based stores and data partitioning and routing of data to the right place, on-the-fly extensibility, all of those, and no joins, for example, no aggregate tables as we have with relational database. All of these concepts are much more well understood now, and people understand the trade-offs that they need to make in order to use these kinds of systems. So they get capacity, they get flexibility, they get scalability, but on the other hand, they need to sacrifice some of their consistency requirements and latency requirements in some cases. There's a very famous theorem which is called the CAP theorem. If you guys have heard about it, CAP stands for consistency, availability, and partition tolerance. And this is much better understood today than it's been before. Essentially, this theorem says that you can only have 2 out of 3. You cannot have, for example, consistency, availability, and partition tolerance together. You can either have consistency and availability, and then you sacrifice partition tolerance, which means that if you want to be 100% available, you cannot survive, or your system cannot be up or available when there is a network partition. And on the other hand, if you do want to support partition tolerance and availability, for example, you will sacrifice data consistency. So people understand those trade-offs much better now. And also implementations of these concepts have been improving and maturing over the last few years. And I'm happy to say that there are a lot of implementations now, including what we do, that enable people to kind of purchase and use those products and understand much better how they work. So after this kind of long overview, let's dive into the details a bit. And this is depicts a typical tier-based architecture that is still to these days pretty dominant with large-scale applications. You typically have a web tier, a business logic tier, a data tier, whether it's relational or non-relational, and a messaging tier. And the interesting thing to note here is that whenever you push data into the system, whenever there's a web transaction, or there's a business transaction flowing from a RESTful API, for example, a typical transaction would actually cross-cut all of these tiers and would involve all of these tiers. It would go from the web to the business logic tier, where we do some sort of processing. Then we might hit the messaging tier to delegate some work to another worker asynchronously, and then we'd save some data in the database to make sure that we don't lose the state of the transaction. And this in turn causes a few bad things to happen. The first one is that the response time across these tiers is limited. There's only so much you can do with this kind of architecture, because there are a lot of network hops, there are a lot of disk hits that you have to go through, and no matter how fast your code is or how fast your database is, when you combine all of these pieces together, this can slow you down considerably. Another important aspect here is that the system is not very scalable, because there are a lot of disk hits all across this flow here. When you write a message to the messaging tier, it typically saves it onto disk. When you write a transaction to your database, it hits the disk drives, and that in turn slows you down very much. The other bit here is that it's also much more complicated to manage, because it's actually the picture you see here is a very simplistic view of things. In reality, it's much more complicated, right? There are load balancers and networks, and storage devices, and a bunch of other infrastructure considerations and resources that are part of this picture. And even with this simplistic picture, you can see that there are a lot of components and moving parts to manage here, which makes it all the more complicated. So once we've seen kind of where we don't want to be, let's talk about where we do want to be. And I'm going to talk a little bit about in-memory computing foundations as we see them at Gigaspaces, and then a little bit about how they fit into this new architecture that we're talking about. And then we'll talk about how this whole architecture and way of doing things fits into the big data stack. So as far as in-memory foundations are concerned, there are three important foundations here. The first one, it's called ultra-high performance, but what it really means is that you put things in memory, and that's how it ties together into all of the things that I've said before. The idea is very simple. Instead of having multiple tiers and processes and products that are doing, each one is doing one piece of your transaction processing of your application logic, you simply collapse all these tiers and run them in the memory of a single server or a single process, right? So within the same process or the same slice that you can see here in orange, you run all of these concerns. So you run your code there, your business logic. You access data by accessing the memory of that server with a few kind of interfaces on top of it to provide querying and transaction capabilities. And you can also do messaging by simply pushing and popping events from your native memory. And this in turn, is much faster because you don't have to hop through all of these tiers and hit the disk whenever we want to process a transaction. The next important thing is linear scalability, right? So if you have a single VM or a single server and you have a lot of data to process, even if your RAM is very big, that's still much more limited than saving things on the disk, which is typically 50 to 100 times larger than your RAM. And what you do there is you actually partition the data or partition the workload across multiple servers. It's in some cases it's called load balancing or content-based routing. There are a lot of names to that, but in essence, what it means is that if you have a typical workflow, say you have an e-commerce website, and you want to process user transactions for that e-commerce website, you don't send all the transactions to a single server. You basically partition or load balance those transactions across many servers. You can do that, for example, based on the product ID. So some of the products you'd process on server A, and then another part of the products you'd process on server B. But for a single transaction, you will not have to cross the boundaries of a single server, and that's what will ensure that things happen very, very quickly, and the system is very scalable. Because as you add more products, you can just add more servers. The last foundation or the last pillar here is high availability. So again, we're using memory-based systems, and the way we achieve high redundancy or fault tolerance is by replicating the data to at least one other server in the network. That's what the gray slices represent here. And I mentioned it a bit before when I talked about network speeds. Essentially what we do is whenever a piece of data is saved into an orange slice, into an active server, it gets immediately replicated as part of the same transaction into a backup server. When a primary or an active server fails, the backup server immediately kicks in and continues to process and work as if nothing ever happened. So this is kind of the foundation of in-memory computing and how we implement them here in Gigaspaces. You'll see what the actual architecture looks like, and if you recall the previous picture from slide number 8, you'll see that this one is much simpler. All the tiers are kind of collapsed. The system is now much more scalable and much more performant because even though we have multiple servers, a single transaction is typically processed on just one server in memory, which is much, much faster. And if we're talking about numbers, that can be anywhere between 10 to 100 times faster and more scalable. So you can do much more even with the same resources and the same hardware. So I'm switching to the last slide, how this whole thing fits into big data and more specifically stream processing. So if you recall, when I talked about real-time big data, I talked about stream processing and ad hoc querying, and we're talking about stream processing right now. And this whole concept of a data grid or in-memory computing is very appropriate for processing large amounts of streams that are flowing into your system. And you can see that as data or events flow into your system, they get partitioned across your instances, which is what we described in the last slide. And each of those instances can actually process those events as they flow into your system. It can update certain counters, for example, if that's what you're interested in. It can make a little bit more complicated calculations. And it can even serve as a front end or interim phase to actually pushing that data into a more persistent storage medium like Hadoop. So the real-time tier here in the middle that is called processing grid basically gets all these events, processes them in real time using all the capabilities we described before, calculates some things that are relevant for your real-time insights that you want to have. For example, the number of users that are accessing a specific product, or the number of suspicious movements coming from a specific sensor, or the number of times a certain URL has been watched. All of these things can be processed very quickly and on the fly. Um, and it can also, like I said, serve as an interim or intermediary layer before shipping that to Hadoop. Um, and what the steer does before it ships things to Hadoop is actually mash the data and transform it to, for example, uniform format, which will later be much easier to process for tools like Hadoop. This will also help Hadoop to work faster later. So I hope this makes sense. It's a lot of information in such a short amount of time. But if there's a key takeaway here that I'd want you to go out of this session with is that in-memory computing is available. It's a proven technology that's been implemented and working for already a few years in the most demanding and strenuous environments, and that it can be used to serve or to process very large amounts of data in very short amounts of time. I hope this makes sense.
Yes, yes. Well, thanks for that, Ray. I apologize. I'm an HPC guy, so I'm going to ask you some hardware questions here just to
All
start.
right.
About the processing grid. Is
Yes.
Yeah, I mean, are we talking racks and racks of blade servers, or is that more of maybe a one, like a 8U kind of device, or does it scale?
It definitely scales, and one of the important premises of in-memory computing in general and our technology, to be more specific, is the ability to run on commodity hardware. So you can start with, I don't know, one or two commodity servers, and grow over time. Basically, scale your system or add more resources as your workload grows. Uh, but it's definitely a distributed architecture that allows you to use commodity hardware.
And then how does Gigaspaces keep all that coherent, right? Because you've got a big memory space, and there are transactions that stay limited, as you said, on an individual
Mhm.
server. But how do they communicate between and make sure that it's all coherent?
Yeah, so that's kind of part of the secret sauce.
Yeah.
So we do support the notion of transactions, and I mean ACID transactions. So ACID means atomic, consistent, isolated, and durable. The D, or the durability, in ACID is achieved by replication. So we don't do like disk durability, but what we do implement is durability by replicating the data to at least one other node in the network as part of the transaction. So if your data does not reside on at least one other server in the grid, the transaction actually fails. And when the primary copy of that data crashes or something bad happens, the backup kicks in and continues to work from there. And the transaction scoping and all the mechanisms that take place behind the scenes um, make sure that things stay consistent, no matter how many copies of the data you have. And typically, most of our users have one or two copies. That's more than enough.
Sure, sure. And then the interconnect between these devices, does it have to be InfiniBand or something really low latency, or is it can you do this with 10 gig Ethernet or something?
Yeah, so some of our users are using 10 gig Ethernet. It really depends on your workloads.
Hmm.
But as they say, the more the merrier, right?
Yeah.
So if we have faster networks, the system would work faster, would be more scalable.
Hmm.
But some of our users are working on a 10 gig networks, and that's more than okay.
Great, great. Well, Uri, could you give me a scope of this? I mean, how big a memory space are you able to accommodate with current customers today?
So we're talking about terabytes
Yeah.
at this point. Um, we have a few deployments that span um, uh, multiple number of terabytes
Hmm.
in the same deployment. Um, but typically when people talk about kind of online work sets, I would say the average is about half a terabyte
Yeah.
of memory. Yeah, like I said, some of our extreme customers are kind of taking it to the higher limits of this. And another interesting thing to say that I kind of didn't mention here is that in the last year or two, we've been aware of another very important, I think, hardware trend, which is solid-state drives. And solid-state drives essentially kind of fill a gap between hard disk drives and memory, in the sense that they they're not as big in capacity as hard disk drives, still because of cost benefit equations, but they do provide much larger amounts of data for the same price compared to RAM. And on the other hand, in terms of performance, they're way faster than HDDs. Okay, and typically, if you access an SSD drive directly, and some libraries allow you to actually access the drive very quickly by circumventing a lot of the things that happen in the kernel space, for example. It can be as fast as 1/10 or even 1/5 of accessing your RAM, and that is way faster than HDDs, which are typically 1,000 times or 100 times slower than the RAM. So if you have some use cases that can tolerate this kind of performance, right? If you're not kind of limited to the sub-millisecond latency, you're okay with a few, like 10 or 20 or 30 milliseconds data access times. SSD can provide a way to further extend your capacity in a much more cost-effective way, right? So you can actually store tens of terabytes of data using the same infrastructure, as opposed to basically buying more and more RAM, which is still more expensive than solid-state drives.
Sure,
So
sure.
this is something that we're working on right now. We have some partners there, and large hardware providers that we're working with on implementing this kind of technology. So you have kind of a seamless continuum between the RAM, the SSD drive, and the HDD drives.
Yeah. Well, kind of a wrap-up question here, Uri. I wanted to ask you about customers that might want to try this. I mean, how do you guys engage with them? Do you have a in-house system set up that you can bring their data in and they can kick the tires, as we like to say?
So sure. So yeah. So this is it's available. The product, the platform itself is available for download and for evaluation. For developers and for implementers. We also allow you to deploy that on the cloud if that's what you want, and basically give it a test drive. We'll actually soon have an offering that allows you to start your own cluster on the cloud, and give it a test drive if you don't want to download and install things. But we're very permissive in the way that we allow people to evaluate this thing. And if you need more than the kind of stock 3 months evaluation period, you can just reach out and we'll give you additional licenses to do that. So as long as you want to evaluate that, go ahead and do that. If that works for you, or if you want some help, just give us a call, and we'll be there to support.
Well, great, Yuri. I think, with the survey results, it looks like a lot of people are going to be moving towards, real time and in-memory computing. So I want to thank you once again for coming on the show today.
Thank you. Thank you very much. It was a pleasure.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of big data.